Okay, folks, so we're going to continue with the result that we started at the last lecture but didn't get to finish. So if we have two integers, they're both not 0, one can be 0, but they can't both be 0, then the least positive integer that could be made as a linear combination of those two integers is the GCD. That's what we're going to prove. All right, so let's let A be the set of all things you can make as a linear combination of A and B. So X and Y can be whatever integers you like, but we want that AX plus BY is non-negative. Then, by the well-ordering principle, remember the well-ordering principle says that if you take any subset of the natural numbers, you are going to get something that has a least element. So A is a subset of the natural numbers. It's everything you can make is a linear combination of integers, so it's going to be an integer, and we're only taking things greater than or equal to 0. So this satisfies the well-ordering principle. So we know that A has a least element. And let's call that D. So there we go. So since we can write D as a linear combination, let's do it. Call it AX naught plus BY naught. Undo that. BY naught for some integers X naught and Y naught. We know it can be done because everything in the set A can be written as a linear combination, so we pick the least one and we call that D. And the X and the Y that make that happen, we'll pull from the integers and we'll call them X naught and Y naught. So now, by the division algorithm, or the quotient remainder theorem, we know the following. We know that we can divide A by D. So by the quotient remainder theorem, A divided by D, so that means that A we can write as QD plus R for some Q and R, which are integers, and R is a remainder. So it is at most D minus 1. And we can just rearrange that for R. So if we look at this, we get that R is A minus QD. But we know D is a linear combination of A and B, so let's fill that in. So we get that R is A minus Q times D, but D is AX naught plus B Y naught. And then let's do just a little rearranging. So we can rearrange this, and we get that R is the following. It is A times 1 minus QX naught plus B, or sorry, it should be a minus, not a plus, minus B times, I'll write it like this, Q Y naught. But let's think about what we just did. Remember, r is a remainder. So if r is a remainder, it means it's less than d, or it's 0. But, actually, sorry I misspoke above and I miswrote as well. So we don't want non-negative. It says up here we want the least positive integer. So let's take them as positive integers. That's my mistake. So we just want that this is indeed greater than 0, not greater than or equal to 0. So we want non-zero, we want actually positive. Oh, what is going on here? What did I do? I think this is fine. Yes, okay. So now, well, we know r is a remainder. So what does that tell us? Well, it says that r is a linear combination of a and b. 1 minus qx naught is an integer. Qy naught is an integer. Actually, negative qy naught is an integer. So it looks like we've written r as a linear combination of a and b. Well, so this means that r can't be in that set. And the only number not in the set A is 0 that r could be. So since D is the least element in A, R must be 0. So what does this mean? Thus, well, let's go back up here for a second. So we're writing A as QD plus R, but if R is 0, we get A equals Q times D. So A is a multiple of D. If A is a multiple of D, that means that D must be a factor of A. So D is a factor of A. And we can just repeat this. I don't want to do the same thing. So similar to the argument above, we know that D is a factor of B. Just write B as, say, Q2 times D plus R2 divide B by D in this case, and repeat what we did above. So, we know that D is a common factor of A and B, which is pretty cool. Now we just need to show that it's the least common factor. So, let's say there's another factor. And we're going to show that the greatest common factor, not the least common factor. We want to show that D is the greatest common factor. So, we need to show that D is indeed the greatest common divisor or factor of A and B. So let C be another common factor. And what does that mean? That means you should be able to write A as, let's say, what? R times C, and B as S times C for some integers R and S. which is great. Now consider, well, we know we can write D as ax naught plus b y naught, which, well, a is r times c, so let's make this rc times x naught, and then this is sc times y naught, since b equals s times c. But we have a common factor of c, so let's pull that out. So that is c times rx naught plus s y naught. But what did we just do? We wrote d as c times some integer. So we can say, since rx naught plus sy naught is an integer, we know that c must be a factor of d. So we just picked another common factor, and we showed that it's always a factor of d. So what does that mean? That means that d must be the greatest. Which is what we wanted to show.